Hello world. Today I have the privilege and the joy of introducing Jonathan Park. Jonathan obtained his bachelor's degree in psychology from the California State University at Fullerton. His passion for quantitative research and pedagogy grew, and he signed up for another couple of years to obtain his master's degree in experimental psychology with an emphasis in quantitative psychology. Since then to now, Jonathan is a fifth year and flourishing in the HDFS PhD program. He is a doctoral candidate co-advised by Peter and Seaman. He is clearly in the right program, as one of the first things Jonathan said to me when we first met is, "Hi, I have this life-changing manifesto for you to read." Jonathan's research gravitates around studying methods for identifying nomothetic trends in idiographic processes. Among his various methodological interests with studying discrete time dynamic network models, his recent work focuses on community detection and fuzzy statistics. Finally, a fun fact about Jonathan is that he takes the model of work hard, play hard to the next level by adding play hard, work even harder. So he does all of this online on Twitch. So if you ever want to chat, his cyber door is open and he streams about research, coding, and just being foxy. And more importantly, sharing strategies to mitigate academic existential pain. So definitely worth the visit. So please join me in welcoming Jonathan.
Cool. Thank you for the really kind intro. I'm going to transition over to this. Again, this is just temporary. This is just a joke because Sharon mentioned my stream, and so we set it up this way. I do stream. Don't go to my stream. Please don't follow me. Don't see what I do outside of school. But I do have a Penn State themed emote if people are interested. This is primarily why I'm sharing screen. You can see that it's this explosion of little weird Penn Stat guys. So I'm going to stop sharing, and then I'm going to share my actual talk now. So my actual talk is on subgrouping continuous processes in discrete time. And there's, several vocabulary words there. So we're going to talk about subgrouping. We're not talking about continuous processes or continuous time processes and discrete time or discrete time processes. A lot of this work started from a question that happened during my individual meetings with Peter and Seamin, where Peter asked the question of what do you think happens to the contemporaneous effects or the fast effects in a VAR model as the delta t or the difference in time approaches zero. And so I ended up going home after that meeting and I looked in a journal for one of the journals of physics, and I found a paper on modeling sound dynamics in neutron reactors. And in that paper, they describe the relationship between a special case of a stochastic differential equation model and a structural VAR model, like a limited case of that. And so it was really fun and cool to see that modeling the sound dynamics of neutron reactors is relevant for also the work that we do. So just kind of emphasizing that you never know where these connections are, and stay curious, folks. So we're going to start by going over several goals. We're going to talk about how processes unfold. I have several examples of how processes unfold, and then we'll talk about how they can be modeled using continuous time models as well as discrete time models. So we'll cover the first or the last two parts of the talk first, and then we'll go into subgrouping methods. And then finally, we'll talk about a simulation study that I hope is motivated from the almost hour-long rant that I'll be doing in the time to come. So big picture, these are kind of like the answers already. Modeling things in continuous time just makes sense. If you can model things in continuous time already, it makes sense to just kind of do that. But discrete time methods are incredibly popular in the behavioral sciences and econometrics. VAR type models are just really popular in general. And so it's obviously hard to get that paradigm shift. I'm going to talk about a lot of reasons why we use discrete time methods, but if you can use continuous time methods, do that. And subgrouping is an area of interest that's really popular and gaining in popularity as we try to focus more on individual dynamics. We also want to maintain this ability to generalize our results. And so if I model myself really well, I conveniently know almost nothing about any other person. So the goal with these subgrouping approaches is to find these common themes that exist between people in how they change over time. And so that's kind of motivated our question of how well do discrete time subgrouping approaches work when the underlying process is continuous. So subgrouping, processes are continuous. I don't think that's controversial. Things change over time, and there's not necessarily like discrete steps in time at which things change. The effects of variables on each other and on themselves changes as a function of the difference in time. So instead of like reading that example, I just have examples later that I'll hopefully be able to illustrate. But in addition to that, looking at multiple studies in the discrete time framework could yield different parameter estimates. And so I'm going to kind of explain what each of these means. So this is just like a simulated relationship that I just made up. We can imagine that there's this relationship between happiness and anger, and that relationship, the regression weight, if you want to think of it that way, changes as a function of the distance in time from when you felt when you felt happy and when you feel angry. So let's say relatively quickly, when I feel angry or when I feel happy, I feel a lot less angry. And I hope that's not controversial to say, but maybe it's the case that when I feel happy, my anger reduces quite a bit. But it also makes sense that 15 days later, a single instance of me being happy might not have a strong relationship to how angry I feel. And so we can imagine that the relationship between happiness and anger is changing as a function of the distance in time or the difference in time. And one thing that's important to note is that this is still the same relationship. It's just that the relationship is changing as a function of that difference. Another example would be in medication. We can imagine that if I give you a drug to treat some sort of symptom, it would be unreasonable for me to assume that the second I give you the drug instantly works and I should see some sort of appreciable effect. But kind of extending on a point I made earlier, if both of us are doing a study and I administer a drug to a patient, you administer a drug to a patient, and I measure the patient about an hour later, I would see that there's a relatively strong effect of the drug on that symptom. But if you then measured 3 hours later, you might conclude that there's almost no effect of the drug. And really, the difference is not that the drug didn't work, but the function of the difference in time, right? So you measured much later than I did. But kind of related to all of this is that these regression weights, these associations all exist in one continuous function, right? So me measuring here and you measuring here doesn't mean we measured a different relationship. We measured the same relationship just at a different delta t or a different relation or a different interval of time. And hopefully to drive the point home further, if you saw this kid just walking on the street who listened to My Chemical Romance in high school and thought that was cool, you might try to make a prediction of this kid's behavior, and you might be accurate in describing this person's behavior the next day. You might be even able to tell what this kid would be like towards the end of the academic year, but you might not be able to forecast that that kid ended up getting a haircut and went to Penn State because that's me. And so you can imagine again that I'm a real person and I exist continuously over time. So the fact that your predictions changed or got weaker doesn't mean that I'm a different person. It means that the relationships change, the importance of variables change. And I want to note, it's not that it's always going to decay, right? We can have like oscillatory relationships that are stronger at some points and weaker at other points, but this is just the examples that I'm running with. So hopefully that motivates the idea that processes change and the relationship between variables can differ as a function of the difference in time. So how do we model things in continuous time? So this is the standard form of a stochastic differential equation model. And I don't really want to just describe everything because you have eyes and you can read it, but really we can imagine that this is our intercepts. This is some sort of drift matrix that relates our scores at the current time, ultimately to predict the changes in our scores, plus some noise, right? So the things that are left undescribed by like our change process here, right? And if you're familiar with VAR models, you can see that this is already really similar to how a VAR model works and looks. But the benefits for modeling in continuous time, I've mentioned several already, but continuous time models can regularly or readily handle irregularly spaced data, and they're not particularly sensitive to our sampling rates. And parameters in continuous time can be transformed to any arbitrary delta t. And I'm not going to explain this right now. There's a slide later where I will explain this in much more detail, but just trust me that we can transform parameters from a continuous time model to any arbitrary delta t and interpret those as var1 parameters. And continuous time networks have seen have drawn some points for special considerations in mediation. So the weights and the roles of a mediator may change because we're sampling them or we're modeling them in different delta t's, and they may actually be represented differently in a continuous time framework. So some hindrances to continuous time models this is more of a, you'll see that this is more of a list of the fact that we just use discrete time models more often, right? So discrete time models are much more popular. They're much more easily interpretable. Not that, like, once you have the hang of interpreting a continuous time model, it's not particularly hard, but you can understand a discrete time model much more quickly on the uptake. Measurements and experiments are typically planned in discrete time. We might measure people once a day or twice a day or, several times a day, but we're certainly not trying to, measure them in some continuous fashion because of things like participant burden. And so this is where we'll draw connections. So I said earlier that a continuous time model's parameters can be transformed to any arbitrary delta t. And what that means is that if I have a continuous time model and its parameters, I can transform it to match a discrete time model at an arbitrary interval of time. So if I have this continuous time model, its drift matrix, which you can think of as being the regression matrix, plus the delta t. So the delta t being what interval of time do I want to look at this at? I can just do e to the a times t, and then I would get the phi matrix or the regression matrix at a discrete time interval. So if I wanted to say, take the continuous time model and say, what does this look like if I measured people once a day? Then I can apply that transformation, and then I would see what the phi matrix or the lagged regression matrix looks like if we were to measure once a day, if I've estimated the continuous time model. And similarly, we can do that with the errors or the residual covariance matrix. We can take this transformation. And what I want to point out here is that we see two primary elements here are kind of informing what goes into this residual covariance matrix and the discrete component, is that we basically see Q, which is our process noise, and we see A, which is our drift matrix. So as we increase our delta T, we're getting more information about our process noise, as well as more information about the drift matrix getting sucked up into that psi matrix. If this doesn't make sense, that's fine. I'll explain this more as we're going. So hopefully the ball is rolling, even if I'm losing you a little bit, but I don't think so. I hope not. So when we model things in discrete time, I've said this several times, discrete time modeling is just very intuitive on the uptake. Discrete time models offer an intuitive way to describe variables and how they relate to each other, right? So if we measured people and we did a discrete time model, let's say on a once a day schedule, we might be able to say that, when I'm happy today, I tend to be less sad tomorrow. And, this is a time average. So that doesn't mean that it's happening all the time. It's not that when you're happy, you will be less sad tomorrow, but it's a time average. So when you're happy today or one day, the next day, you tend to be less sad. And so there's this intuitive way of explaining like those kinds of var type relationships. And I've said var a lot of times, and I realize that I haven't really described it, but the vector autoregression is what a var model is, and we'll be describing it in the coming slides. But essentially, it's a model that describes how variables are related to themselves and each other at discrete steps in time. And it's very popular in the behavioral sciences, in econometrics, and other fields. There are some limitations to discrete time models. The results aren't necessarily comparable across studies, right? So if we have variability in when we sampled our data, we might find that the relationships appear to be different or almost non-existent in some studies. But really what's happening, if I can come back to this slide, I think what could be happening is that the association is just weaker at a different delta t, so at a different interval of time. So if we don't get our measurements consistent, then comparing across studies or the parameters across studies could be difficult or confusing if we're not explicit as to how the measurements were taken and when they were taken. Discrete time approaches also assume equally spaced measurement occasions. So the example that I just used about when I'm happy today, I tend to be less sad tomorrow. If I don't consistently measure once a day at approximately the same time, then I'm going to be getting weird kind of associations. Right. So if I measured people like once in the morning and then once at the next evening, then that's not once a day anymore. And so the interpretation should be adjusted for that. But then if we're doing that consistently over a long period of time, then we're completely messing up our interpretation. There's also special considerations that need to be made for discrete time models if we have faster effects. So this example that I've been running with, when I feel happy, today I tend to feel less sad tomorrow, doesn't take into account that when I feel happy, I tend to feel less sad almost immediately, right? So while there may be a carryover effect from day to day, there certainly is a faster effect that also exists where when I feel sad or happy, I'm less sad almost instantaneously, or within the span of minutes, maybe even hours. But certainly it doesn't take me a day to feel less sad. So while there may be carryover effects that we model from going day to day, there's still effects that happen much faster than that. And you can think about, I've been using the affect example, but we can also think of neuroimaging if we're modeling kind of brain regions and how brain regions are interacting and communicating with one another. An fMRI scan can take, say, upwards of like a second or 2 seconds per image, but hopefully your neurons do not take 1 to 2 seconds to fire. And so the communication between regions of the brain is significantly faster than the way that we gather that data. And so it's important that we kind of take into consideration that there are faster effects. And if we think those faster effects are there, attempt to model those. So there are some special configurations of VAR models. The two that I'll be talking about in the coming slides are the graphical and structural VARs. And they can be used to model those faster dynamics. I realize I just clicked out of my slide. So if you've ever seen any presentation that I've given, I've used this figure like 1,800 times. Way to go, first year, Jonathan. So this is a visual representation of a VAR type model. We can see that variable 1 and variable 2, let's say happiness and sadness, are predicted by happiness and sadness at 1 step previously. So unlike the continuous time model where it's just the changes or the derivatives or the differentials in the set of scores, here we have an explicit mention of a discrete step in time back, right? So it's t minus 1. So it's right now and the previous occasion. So this can be a day ago, it could be a month ago, it could be a year ago, it could be whatever, but it's still one discrete step back in time to describe this association. And so we can see that there are these relationships between the variables in themselves as well as each other. So happiness can predict itself, or it can predict sadness. We can model this using the VAR model. I've written it here, and you can see that it's somewhat similar to the continuous time model. Hopefully, again, I'm just going to kind of summarize this. We have our intercepts, kind of like your starting points or your kind of home bases, plus some regression coefficients matrix multiplied by your scores at the previous time. So we're predicting your current score by where you tend to be, plus your previous score times some regression matrix. And then we have this kind of noise, these process noises, or these residual vectors. And here I'm going to say that the residual vectors are assumed to have zero means, be normally distributed with a covariance matrix of psi star. And so this is where the psi star came in when I was talking about the continuous time models. You can see this psi star here. And again, it's going to be a product, if we have the continuous time model, it's going to be a product of A, the continuous time drift matrix, as well as Q, the process noise. Cool. So what happens when we're modeling? I want to make sure, yeah. So what happens when we're modeling a VAR model and we have those faster effects that I mentioned, right? So this part of the model here is going to describe where we typically are, as well as the regression coefficients that will help us transform our previous state to our current state. But if after using this, we don't account for all of the variability, it'll be sucked up into our residuals, right? So our residual covariance matrix will have additional information of effects that are faster that we didn't capture with our dynamics here. And so if something is happening faster and it's not described by mu or phi star, then it would be sucked up into psi star, and we can model those. We can model the residual covariance matrix. So this is one such example. And you might notice that this looks just like the VAR model, but the difference is that we have this bar that exists between two variables in the same moment. So again, if we just imagine that this is happiness and sadness, we still have the lagged effects of happiness predicting itself at the next time point, happiness predicting sadness at the next time point, etc. But now we have this contemporaneous correlation. So contemporaneous effect is exactly, I've been saying faster, it's the same thing. In this case, what this is describing is the relationship between variable 1 and variable 2, happiness and sadness, within that lagged effect, right? So if this is once a day, so then this is yesterday predicting today, then this correlation describes things that happen faster than once a day, right? And really, you can take that by fitting a Gaussian graphical model to the residual covariance matrix. So if we have the residual covariance matrix, we can invert that to get a set of, or we can invert that to get K, which is the inverse of the residual covariance matrix, or the precision matrix. And then we can apply this transformation here using elements of K to get what are essentially partial correlations, right? So then this bar is a partial correlation, which tells us that variable 1 and variable 2 are related kind of after conditioning on all other variables in the system. So this is a 2-variable case. If we want to imagine that there's a third variable, so if this is happiness, sadness, and let's say there's a third variable of anxiousness, if there's a bar between happiness and sadness, you're basically saying that there's a relationship between those two after conditioning on anxiety as well. And additionally, we can standardize our lagged effects as well. That's why the notation changed. Instead of phi, this is PDC, but really this is just a standardized form of just the regular phi matrix. So really the important part of this that I want people to take away is that we can model partial correlations between variables. by modeling the residual covariance matrix. One thing that's important is that this may not be like sparse, so then we'll apply things like lasso regularization to help shrink down parameters and make it sparse. So one thing that I want to go back to here is we might be interested in modeling faster effects. So the effects of happiness and sadness on each other, day to day, but then we'll acknowledge, what? Happiness and sadness affect each other much more quickly than once a day. But we might also think, is that relationship balanced, right? So because this is a bar, implicitly it's a correlation. It's saying that there's a relationship between these two, but we're being agnostic as to whether there's a direction to this effect. But at least for me, when I feel sad, I feel much less happy very quickly. But when I feel happy, I might not feel less sad. Right? I can have like a moment of happiness that doesn't persist. And so there could be a relationship going from variable 1, happiness, to sadness that's weaker than the relationship from variable 2, sadness, to happiness. And so in those cases, I might not want to model this as a correlation. And there's a solution for that. So this is another way of modeling those faster effects, or these contemporaneous effects, being the structural VAR model. And so here, it's the same thing as the VAR model. It's not the same, but it looks similar to the VAR model. We have these lagged effects again, but now we have these contemporaneous effects. However, now there's a contemporaneous effect of sadness to happiness, as well as one from happiness to sadness. So they don't necessarily have to be the same in magnitude or weight anymore. To model with the structural VAR, we can use this equation. So here, again, we have mu, kind of where you tend to be, as well as this lagged effects, right? So this is what we've seen in the VAR models already, and our residual vector. The thing that's added in the structural VAR is phi naught, or phi 0, which is saying what is the relationship between variables in this time step to this time step, right? So this is what is yesterday's effect on today, but this is saying what is today's effect on today. And one constraint that is applied to phi 0 is that the diagonal elements are fixed to 0, right? Obviously, your happiness right now predicts your happiness right now because they're the same thing. So we'll fix the diagonal elements to 0 in phi to stop that from happening. As well, the lag effects are pretty normal. They can be completely full. And then our residual vector is assumed to be mean 0 normally distributed, as with the regular VAR model. But now the residual covariance matrix is fixed to be diagonal in the case of gimme, which I'll talk about in a bit. So by doing this, we're assuming that the effects, the off-diagonal relationships that were in psi star are now being modeled in phi 0. So I had an earlier slide where I said these models are similar and can be transformed. So this is just showing that again, but more explicitly. I'm going to zoom in a bit. So here we have this true A matrix being the true, if you want to think of it as the regression coefficients matrix of the continuous time model. So if we have this model here with these parameters, so we have a 4-variable system and these variables are related by these weights, and we apply this transformation, right? We exponentiate A times delta t to get phi star at that delta t. So let's say I wanted a delta t of 10. So maybe I want to look at what does it look like if I measure every 10 days. I don't know why you do this, but if you wanted to, we can get what the true phi star is, right? The true A transformed to the true phi star at that delta t. And what we notice is that a lot of these effects get attenuated, so from 0.9 to 0.06. And we also see effects that like pop up that aren't actually there in this model. So it's not that those effects aren't there, it's that by transforming this, the representation of phi star at a delta t of 10 looks like this when the true matrix or the true drift matrix looks like this. I'm not going to go over these additional transformations, but with the structural var, you can turn that into a regular var model using these transformations. And then with the graphical var model, I noted earlier, the graphical var model is just the var model with some transformations applied to it. Does anyone have questions? I know this is a lot of info. So we're going into subgrouping and it's like a completely different pivot. Okay, I'm not seeing anything. Cool. So we can talk about subgrouping in discrete time. So the goals of subgrouping, we want to find how individuals change over time. And we can, assume that people in how they change over time are somewhat unique, right? When Sharon introduced me, she said that I tell everyone about Peter's manifesto if they've never heard about it. People change uniquely over time all the time. The way that I change is not necessarily going to be the same as how other people change in their emotions or in a whole lot of other features. And so if I said this earlier as well, if I model myself really well, that doesn't necessarily mean I know any other person's dynamics at all. So with this increased focus on modeling individual dynamics, another interest is, how can we model individuals, but still find things that are common to groups of people, right? So if I want to diagnose people based off of, common dynamics, I might want to find dynamics that are kind of prototypical for depression or prototypical for people who are at risk of suicide and stuff like that. So it might be useful if we can find kind of dynamics that characterize the prototypical way that people change. So I'm kind of merging these two. So commonalities exist among some groups of people. So I'm citing Peter Coopens' work on emotional inertia in people with major depressive disorder or people with just depression. Doesn't necessarily have to be major depressive disorder, but if we think about the relationship between, let's say, how sad or how depressed you feel yesterday on your depression today, people with high emotional inertia would have strong autoregressions, right? So if we think about this really simply as this multiplied by 1, right, predicts variable 1 or variable 1 at time t. So then if this value is closer to 1, then this isn't going to change very much moment to moment. So if I'm depressed times 1, I'm still depressed. So what we mean by emotional inertia is that these coefficients are relatively close to 1. They're higher than say controls. And so when I'm depressed, if this is like a 0.8, it'll take me a long time to come back down versus like healthier controls who do not have depression. There'll still be like a positive association most of the time. It'll still be when I'm depressed, I tend to still be depressed the next moment, but hopefully it's lower in people who are controls as opposed to people with depression, where that's kind of a characteristic of being depressed, is that you have this kind of momentum in your depression. It like carries forward. So there are commonalities between people, even though a lot of the time our dynamics can be quite heterogeneous. So with subgrouping, we want to identify those kind of common features if they do exist. So that's just what that last bullet point is saying, except it's being written in science, right? So identifying homogeneous subgroups of individuals who share common dynamics, find groups of people who change over time similarly, right? Their dynamics are similar over time. So we can use this example here. I've used this in a previous talk, ignore X, but basically if there are people who are similar, you can imagine that I would want to group the sad faces together, right? And I would want to group the people with anxiety together, right? If these people have similar dynamics, let's say, and these people have similar dynamics, and there's features associated with them that distinguish depression from anxiety, we would want to separate out those people. It's not always going to be the case that it's going to fall along neat diagnostic lines, but if there are features that characterize a certain group of people, we should find those features. So I'm going to talk about, I don't know why this section is called this section though, but you can ignore the title. But we're going to talk about two discrete time subgrouping approaches that are based off of those models that I talked about earlier, right? So the graphical var, we have the chain graphical var with subgrouping, as well as SGIME, or the subgrouping option in the group iterative multiple model estimation procedure. So I'm going to kind of not go into super detail with this because I'm kind of running up and I want to get to the simulation study. But the logic of both the chain graphical var models and SGIME, in this case, I'm just describing GIME, but the logic of these two models is really similar, right? So we start by fitting a model to everyone, right? So we look at how are my dynamics different over time. We'll look at how are Sharon's dynamics different over time. We'll look at Jay's dynamics. We'll just fit a model to each person, a graphical var. So we're modeling the lagged effects as well as those contemporaneous correlations. And then we create what's called an adjacency matrix. I'm actually just going to skip ahead. This is an adjacency matrix. What we see here is basically just a count, right? So you can see the diagonal elements are 0. This would normally just be how many things do I have in common with myself? We don't really care about that. So we'll just 0 that out. And then we'll see this 15. What this means is basically if you think of rows and columns as subjects, then what this tells us is that subject 1 and subject 2 have 15 things in common. Now, what those things in common mean depends on you. In the case of the graphical var, let's go back to that model. Common, or things that we have in common, are going to be these parameter estimates, right? So in this case, this 2 variable case, we'll have 1, 2, 3, 4, and 5, right? So we'll have 5 possible things that we can have in common. And so if I have PDC 1-1 and J has PDC 1-1, and it's also, and both of us have a positive value, then that'll count as a similarity. If I have PDC 1-1 and CMIN does not have PDC 1-1, we don't have that in common, right? So we wouldn't count that. And so we basically construct an adjacency matrix based off of our var models, or our graphical var models in this case. And we basically apply a community detection approach. In this case, we're using WAP-TRAP, and we're trying to find groups of people who are more similar to each other than they are by chance. I'm not going to go into detail as to how WAP-TRAP works, but it does an okay job. There's some issues with it, which is why we added these extra steps, but it doesn't matter for like the kind of broad strokes discussion. But essentially what we're doing is we're fitting var models, we're creating a similarity matrix, how similar are people to each other, we're searching that. And then what we get are groups of people who are more similar to each other on their dynamics, right? These people tend to have the same paths, and those paths tend to have the same valence. They tend to be, like positive regression coefficients or negative coefficients. And then after that, we basically put people in a group, chain them together, and then we fit a graphical var model to the change time series of all those people. GIME is similar in a way. There are unique differences. So GIME starts by fitting what's called a null model. In this case, it's where the autoregressions, the lagged effects of the variables on themselves are freed up, as well as the diagonal elements of the residual covariance matrix are also freed up. So that psi matrix, the diagonal elements are also freed there. Then it'll check modification indices, and it'll add a parameter that improves the model fit for a majority of subjects. So this is just the regular GIME stage. And it does that again and again until it can't improve everyone's model. How is graphical var different from fitting a var model with lots of variables? So really the difference between a var and a graphical var model is going to be that you will get these contemporaneous correlations. So if you fit a var model and then you apply these transformations, this to the phi matrix, and then you get these from the residual covariance matrix, and inverting it, you have a graphical VAR model. The graphical VAR model is just when you're using the inverse of the residual covariance matrix. I don't know if that answers your question. Thanks. Okay, cool. Thank you for the question that you said you would ask, that you told me you would ask me. So we'll basically check the modification indices and see, can we add this parameter? Does it help a majority of people in describing their dynamics? And then after the point that we cannot improve the majority of subjects, we'll just start pruning the paths. So here I should have updated this. What happens after this is we basically look at every individual's model so far, as well as parameters that we could add. We still look at the modification indices for each subject, and we do the same thing. We create an adjacency matrix, and then we look at how similar are people in their dynamics. And Gimme uses a similar logic. It'll look at the sign of the effects. Is it positive for both people? Is it negative for both people? As well as the direction of the effects, where it's relevant. And then after that, it groups them together. It creates subgroups of people, and then it'll do this search again, with the only caveat that the null model is now the model that was derived at the group stage. And then it follows this exact thing. This percentage changes from 75 to 50%. By default, you can change it. And then after it's done that, it'll move forward, and then it'll fit individual models to people. So then with Gimme, you get that group model, subgroup models, and individual models. So I don't know why I have this, because I already described it. Here's the verbal version of what I just said. But yeah, we're using those contemporaneous effects, that phi 0, as well as those lagged effects, the phi 1. So if we go back to this figure here we have 1, 2, 3, 4 effects possible, plus 2 contemporaneous. So here we have 6 parameters that we could have in common if we are entirely the same. If all of us had non-zero this, all positive, and these all positive, then we would have 6 things in common. Okay, so now we're at the simulation study. We're close to the end. So we had 2 questions when we did the simulation study. So given that we model things in discrete time quite often, if the underlying process is continuous, how well can we recover true subgroups when the underlying process is continuous? And how well do we do that across delta t? And we'll call these effect sizes for now, right? So as the sampling interval gets bigger, how well are we recovering the subgroups? As well as the actual parameter estimates get bigger, how well do we do in recovering the subgroups? And we also looked at, do differences in delta t and effect size relate to differences in bias and variation in the parameter estimates? So, oops. Okay, so we simulated 100 Monte Carlo runs per condition with 10,000 time points simulated at a temporal resolution of 0.1 seconds. So we basically simulated data at a very small intervals of time. And then what we did was we basically sampled the last 14 or the last 100 time points from the time series at these delta t's, right? So one thing that I want to note is that these 10-second intervals measuring the last 100 time points is going to measure more of the time series than 0.1, right? But that was a decision that we had to kind of go with. So we measured 14 of the last time points at 0.1 seconds, 0.5, 1, and 10 seconds, as well as the last 100 time points at these intervals. We simulated 50 people, 25 of which belong to one subgroup and 25 of which belong to another subgroup. And then these were our effect sizes. These are basically parameters in the drift matrix. Then they just got progressively stronger in 0.3 increments. We simulated a 4-variate Ornstein-Uhlenbeck model, or an OU model. I haven't introduced this terminology, but we can think of it as a continuous time analog for a VAR model. And these are the kind of the data generating matrices. So here sigma stands for these weights, right? So it was either 0.3, 0.6, 0.9, or 1.2. And then alpha was just the common path. So it was still the same value as sigma, but you can see that both groups had this alpha parameter. But in this case, we had sigma here that was positive and sigma here that was negative. And then the other sigmas were just in unique spots. So to tell the difference between these two groups, we have to be able to tell that this group has a positive coefficient, whereas this one has a negative one. And then this is 0 for this group where it's not for this one, and same for this, right? So these were just the drift matrices that we simulated. And so we can go into our results. We basically sampled the data, we fit the graphical var model or the chain graphical var model as well as SGIME, and then we looked at the results. So I'm going to zoom in quite a bit. We can see here we have t equals 14. So when we only measured 14 time points, when we measured 100 time points, and then this would be 0.3, 0.6, 0.9, and 1.2 for the cross-process weights. And what we see here is the ARI. So ARI is just like a clustering coefficient. It's telling us how well are we recovering the true group memberships, right? Because we simulated the data, we actually know this. And you can see that with only 14 time points and relatively weak cross-process weights, we do a horrible job across the board when we only have 14 time points. But when we go up to measuring 100 time points, we see that there's this gradual improvement as delta t here at the bottom, as the distance in time goes up, right? So if we measure very sporadically, or as we measure more sporadically, we're getting better accuracy in the chain graphical var as well as SGIME. Now 0.75 for the ARI is considered like a kind of heuristic cutoff. So we can see that around a delta t of 1, the chain graphical var starts to do somewhat well. And we see this relationship kind of continue across, like as the regression weights get stronger or the cross-process weights get stronger, the effects become easier to detect sooner at smaller delta t's, right? As well, measuring going from t equals 14 to 100 time points, we gain more statistical power to detect those effects as well. So we see that it kind of rises up. Now, one thing that seems kind of strange is that by measuring slower, we're getting more accurate results, right, in the subgrouping side. So the question might be, why is it that we're getting more accurate results at a large difference in time? So if you think, why am I able to tell the difference between people when I measured their happiness and sadness once every 10 days, right, in 10-day intervals relative to like once a day? So hopefully I can tell you a convincing story that describes that. So here we have the biases and the point estimates. And I want to really focus in on like these examples. So let's just say that, let's just focus in on here. We see almost a flat line for both of these models. It looks like the bias and the lagged estimates are basically consistent almost over time. In reality, what happens when we look at the data is that initially in these small delta t's, it's actually just incredibly difficult to pick up those lagged effects, right? They're incredibly weak. And so shut up. My iPad started talking to me. So what happens is that these effects are incredibly difficult to detect, but they are non-zero. So what's happening is that we're basically underestimating the true effects, but we're just saying most of the time, SGIME and graphical var are basically saying there's nothing there. Then as we get closer to a delta t of 1, we actually start getting estimates. Graphical var and GIME are estimating values, and they just are slightly biased, but not super biased. And then as we go up to a delta t of 10, I mentioned earlier when I showed the transformations, the elements in the phi matrix get progressively weaker in our case, shrinking towards 0. So what's happening is that now here we're basically saying, again, everything is 0. But now we're correct, right? Now we're correctly saying everything is 0. So here there's true non-zero effects, but they're really hard to detect. So we're saying that they're 0. And then we're getting more accurate as to what the true effects are at that particular delta t. And then everything becomes zero again. Everything kind of washes away. Now, what happens to those effects as delta t gets large is that they get pushed into the psi matrix, right? So we said that faster effects will go into the residual covariance matrix, and we see that reflected here. So again, initially, it's really hard to detect the effects in psi with these two approaches, but as the delta t goes up, it becomes progressively easier to detect those effects because they're accumulating over the size of that interval until we hit a delta t of 10 where we have almost a relatively unbiased estimate. Oh, I guess this is still biased, but we're getting relatively unbiased estimates at the large delta t. So what this shows relative to the previous slide is that one of the biggest advantages of these two approaches in the discrete time framework relative to VAR models that don't look at the contemporaneous effects is that as that interval is increasing, and we are modeling that psi matrix, a lot of the dynamics are being put into that psi matrix. And since these two models look at the and model the psi matrix for contemporaneous effects, we see that getting picked up. So we're getting almost like a second chance to pick up those effects, and it makes it easier to detect these differences at those larger delta t's. Similar with the RMSEs in the phi matrix, we're basically seeing that they're relatively consistent over time. There is a slight bump. In the small t conditions, basically what we ended up seeing is that Gimme would like erroneously fix paths. This is kind of like how the algorithm just works, is if it erroneously sets a path early on in the group or subgroup stage, it becomes impossible to remove it at a later stage. But we see that kind of at the larger t values, it's somewhat consistent. And then with the psi matrix, the RMSEs tend to go down over time. And so we're kind of seeing that similar thing, that we're getting less variability in the parameter estimates, as well as more accuracy as well. So I've mentioned this in my individual meetings with Seaman, Zach, and Peter. I read Kihai's paper on like modification indices, and the way that he framed his simulation study results was just repeat the question and answer it. So how well do discrete time approaches identify subgroups across delta t and effect sizes? They do well. I mentioned as delta t goes up, we do a better job at separating out those group differences. But the reason why is because we're modeling those contemporaneous effects. And as the effect sizes go up, they become easier to detect sooner, right? The differences become easier to detect sooner. And the differences across delta t and effect sizes relative to bias and variation, or the RMSEs, we see that the point estimates tend to be unbiased, but there's this weird picture in the phi matrix where it's hard to detect, so we're getting it wrong. But because they're so small, the effects are so small, we're not missing it by a lot by just guessing zero. And then as we go up to a delta t of 1, we're getting pretty unbiased estimates. But once we go to a delta t of 10, everything is almost zeroed out already anyway. So then it becomes hard to detect again. Whereas with the psi matrix, we just progressively get better at detecting those psi elements as they accumulate over those intervals. And then with the RMSEs, they're relatively consistent for the phi matrix, but improve. So there's less variation, and we get a little more accurate for the psi matrices. So I think we said this in our paper as well, but if you can model these things in continuous time, if we had just fit the OU model, we wouldn't have to do all those transformations and look at the different delta t's. We could just do those transformations. And so in reality, these processes are likely unfolding in continuous time, but we don't measure them in continuous time. So there's this, I mentioned inertia before, but there is this inertia, this resistance to adopt it. It's slow, but if you can model things in continuous time, it would be beneficial. But hopefully this shows that even if you have to model in discrete time, or if you model things in discrete time, we can still get valuable insights. We can still see what the differences are, but those differences, again, might not be comparable across studies, because you might sample slightly different intervals of time. And it might require that you be wrong by quite a bit before you can see what those differences are if the effects are relatively weak in the continuous time model. Some things to consider, the algorithms for reconciling group, subgroup, and individual differences in dynamics in continuous time framework are still being developed. Siwei has a paper on dynamic mixture models that I can share if people are interested, but you can certainly do that. And these clustering approaches can be applied relatively easily to continuous time models. Clustering can be done on different parameters as well. So here I mentioned that we just look at, do you have this path or not? But I also mentioned that people might have inertia, right? So this phi value, people with depression might have depression and then the same amount of depression the next day. That is, this value will be close to 1. But I also mentioned that when I'm depressed, and hopefully I don't have major depressive disorder, but when I'm depressed, I also tend to be depressed the next day, right? So for my value is also positive, just like someone with major depressive disorder. So the distinguishing characteristic may not be whether I have this path or not, but it may be the difference between us, right? The magnitude of the difference, let's say from 0 or from each other, right? That might separate two people. So it's important to keep considering how we can cluster on different parameters in VAR models to find differences between people. And that's kind of my talk, I guess. That's it. I don't know if people have questions, comments, concerns, insults. I did plan on doing this. I'm going to put these next to each other and then we'll see. I don't see anything right now. So I'm going to put these here.
There's a very good question that asked whether it's hard being this cool.
Oh, someone asked that?
Yeah.
Thank you for the softball question. I'm not cool at all, so I don't know. I can't actually answer that. That's actually a hard question because I don't know. I'm having these 2 QR codes up. This is to our preprints for the graphical VAR paper. So this describes the algorithm that we use for the subgrouping. And then this is the manuscript for subgrouping in continuous time. So if people want to whip out their phones and scan these, feel free to. But yeah, if people have questions, if I did something, yes.
I have one question. So in your simulation, the time unit like 0.1 or 1 is kind of arbitrary one, is it right?
Yes, yeah, they're totally arbitrary delta t's.
So then can I understand, like, if we measure emotion every 3 hours, then we don't really know how much this time interval is slower or faster than the actual dynamics of emotion. Can I understand like that?
Yeah, like we wouldn't know. I mean, I don't think we still know what the dynamics of emotions are or what the time scale is. And so yeah, so like this is relative to some true thing that we don't know in real life. But we can have like educated guesses and we can. Yes, Tim.
Okay, thank you.
Hey, thanks. Always fun to watch, to listen to you talk about this stuff. So one of the, I guess 2 questions. The first question, the way that you talked about sort of discriminability across timescales, right, as you measure more closely or further apart, reminded me a lot of Timo von Ortsen's power equivalence work. And I'm wondering if you could just theorize a little bit about what implications this kind of shape has for measurement. That is to say, if I'm going to run a study and assuming I have in my head some kind of continuous time model, what does that tell me about what I should pick as an optimal measurement interval? Or can I use that to pick an optimal measurement interval to be able to like maximize my ability to spot the effect?
I want to ask
make sense?
first, can you restate the paper that I need to find?
It's called Power Equivalence. It's Timo von Ortzen. And he's talking in a very simple, in his first paper at least, he's talking about growth curves and trading off the amount of time between measurements against the number of measurements against, how long you have to keep your lab open to get enough power, and all of those kinds of things. But one of the things that he's interested in there is like, what's the best sampling rate if you've got to have a lab study, for example, and bring people in somewhere between once a week, once a month, once every 3 days, whatever it is. Like, how do you get the most power out of that for the for essentially as cheaply as possible? Mike Hunter just linked the DOI in the chat if you're interested.
Oh, thanks, Mike.
So I mean, thinking from that perspective, right, and knowing what you know about these kinds of models, is there likely a way we could use this to make a guess at what our optimal sampling interval would be, given a set of constraints or given a set of costs, or a likelihood that participants burn out and throw their phones through the window because they're so tired of answering the friggin' question? Do you think, like, is there a way to approach that? I just want to hear your thoughts on it, I guess.
Yeah, I don't know. I feel like I've been sold on fit the continuous time model if you can. But obviously there are challenges with fit the continuous time model if you can.
Well, but we can't measure in continuous time in almost every case, right? So even if we're going to fit the continuous time model, and I have a question about that next, like, could we use this to tell us about how to measure?
I'm not sure. I guess like I think you could target I'm thinking about this like as narrowing down on a window. So like when we fit these models before with like contemporaneous effects, say on like affect, I think the fastest data set that I've looked at is had like 8 measures a day. And even then it was still like mostly contemporaneous. So I think it'd be interesting if we had a data set that measured people an obscene amount of times a day, and we could fit these models until we found that the contemporaneous effects were relatively sparse, saying that like we found like our interval of 1, our discrete interval of 1. But I don't know that you would be able to like select the optimal based off of our results or based off of just the model. And like, I don't know, because there's a lot of stuff that's also lost. Like we're getting like clear differentiation between the groups, but like how useful is it to know that like people are different and have this weird, almost entirely contemporaneous effects? But like now everything in the contemporaneous effects just describes everything that happens faster than like an interval of 10. So then like you can't really like narrow down like what the right, because like the window is so big for everything that happens faster than that interval. So I don't know that you could work backwards in that sense to find. I feel like it would make more sense to have too much data and then try to subsample that until you could find like your var model if you had to. But then in terms of
a different phrasing of this, rather than thinking about do we collect more data, because always, of course, we want to collect more data. Like, assume we can measure a person X number of times, right? We have some ability to measure, I don't know, 10 people 100 times each. When? Like, how frequently do we want to measure them? Do we want to measure them 100 times in a day? Or, over 3 days or over 2 weeks? Like, because it seems like one of the things you're getting here is like, at different measurements, you've got more precision on some of the paths than on others, right?
Yeah, it
like,
basically
so could you build a trade-off curve? Like,
so
could you,
I see. So like a trade-off relative to the, let's say, accuracy compared to like the biases in the estimates.
For example.
I think you could, definitely. Are you a reviewer on our paper? You gonna make us do it?
I will not yet, but I would look forward to the paper when you do. Yeah, I would think about that. I'd take a look at Timo's paper. The other thing I was just hoping you could talk about for a minute. One of the things that I keep coming back to when I see people transforming back and forth between continuous time models and discrete time models, how strong do you think the assumption of stationarity is there to be able to do that cleanly, right? Like, so if I'm coming up with a daily effect, right, or a 1 day lagged effect, what I'm really getting there is an average of all of the different sets of effects that are happening across that whole day period. If I do it as a continuous time model, I've got to assume there's one process that's continuous, that's happening the same way all the time, right? Instead of like, it moves a little bit faster while I'm awake and a little bit slower while I'm asleep, but it sort of averages out to this. How big an assumption do you think that is, and how much do you think that's going to matter in real data?
I don't think I can confidently answer that. uh, can I tap Mike? I think. Hold on. Let's see. I don't know. I think. Right. So you're asking like if there are changes that aren't. So like if the transformations don't necessarily describe that var process at that particular delta t because of the non-stationarity issue.
Yeah, I mean, if we're dealing with a multi-timescale process instead of a unit-timescale process, right? So there's variability in the paths essentially,
Yes.
right? Possibly systematic, possibly not. I don't think that matters all that much at this point, right? Do you like, how is that going to affect your transition from a continuous time model where you're assuming a stationarity, like down to the instantaneous level, versus a daily measure where you're essentially averaging across a whole bunch of these things, a whole bunch of different time scale effects?
Yeah, I don't think I can confidently answer that. I'm not quite sure.
I mean, that's fair. I don't know either. I was just hoping you could give me an answer.
Yeah, no, I'm not entirely sure. I know that I remember talking to Jay during their or right before their dissertation defense about that same issue of like having stationarity in one time scale may not be stationarity at another time scale. I don't know. I think that would be interesting. I'm sure someone has the answer, but I do not.
Okay, thank you very much. Appreciate it.
Thank you, Tim. Is that it? Can I stop sharing? Am I safe now?
Yeah, Mike. Yeah.
Oh, Mike has a. Hello, Mike.
Hello. So again, like Tim, thank you for the talk. Enjoy hearing about this. I have kind of an out there question. So a burgeoning area of research is sort of in physics. The physics is on the nature of time, and sort of wondering if it is in fact continuous, or if there is sort of a quantized discrete time scale that is fundamental to the nature of universe. If there is a discrete time scale that is part of the universe, how does that affect what you're doing and how you're modeling?
I mean, like even when we simulated the continuous time models, we had to pick like some resolution ultimately for how we simulated the data. So I imagine that like if there is like a temporal resolution to the universe, it's like in the magnitudes of like femtoseconds. And so I think like using a continuous time model would still be good enough for that relative to I feel like like I don't know. I especially like for our applications, I don't think we're going to ever have issues where we run into that lower barrier, and that assuming that there's some continuity in time would be fine.
Well, the way in which my question is serious, and it's meant only half seriously, is there's often an assumption of like, oh yes, well, like the real nature of the universe is continuous. The real nature of reality of this process is that it's going on continuously, that you could sort of slice it up and dice it up at any time scale, no matter how fine, and theoretically it still makes sense. Whereas there really might be a time scale for
Emotion that is too
or emotion
fast.
processes that is shorter than they are actually happening.
Yeah,
Where it
I
just doesn't make sense to have emotions happening or changing, even theoretically, 1,000 times per second.
Yeah, I know that this happened in Jay's dissertation. They had like affect ratings that were controlled by like users' joysticks, and they were measured very frequently such that they binned the measurements instead. And yeah, I think depending on the process, there could be things that we're measuring too fast. At least like I can only speak from like the data sets I've worked with where even with like 8 times a day, we were still getting mostly contemporaneous networks. And so then in those instances, I don't think we're at a
Not there yet.
place with affect in like survey results where we'll ever get there. But I think with those like instantaneous, or not instantaneous, but those like really quick measurements, I guess the question have to be asked of like, are we, I guess it's also like about an operational thing of like, what are we actually measuring when we're measuring that fast? Is it still emotion or affect, or what is it? What is it we're measuring now? Subscribe to Mike's measurement class to find out more. But yeah, I think I don't know. I've always really liked those ideas and like the theory of measurement of like, but I've never thought about this since I got here of like adding that time component of what if we're measuring too fast? Because it's usually that we're measuring too slow, but like now that we have like accelerometer data and like other kinds of data that we're gathering on much more continuous, or closer to the faster end of like how useful is this data when we measure it too quickly. So yeah, I don't know, but I think it'd be interesting to simulate data in that way of, I mean, at least in our simulation, when we simulated faster than 1, we tended to, or like in interval of 1, we tended to just get worse and worse results as we got closer to the continuous time model, in which case we would just fit the continuous time model.
Cool. So today's
I like
questions
Tim's
are really
question.
thought-provoking. Yeah.
I like Tim's comment. Congrats to Mike for asking a question even more out there than mine.
Okay, we're running out of time, so I'm gonna stop recording.